Hi friends, welcome to SV Technology. In this video, we are going to discuss about micro operation or micro operations in COA subject, Computer Organization and Architecture. ఇది కూడా ఒక వెరీ ఇంపార్టెంట్ క్వశ్చన్. ఈ క్వశ్చన్ కంపల్సరీగా మీకు ఫైనల్ ఎగ్జామ్ లో వచ్చే ఛాన్స్ ఉంటుంది. కాబట్టి మొత్తం వీడియో చూడండి. దానికంటే ముందు ఈ ఛానల్ ని ఫస్ట్ టైం విజిట్ చేస్తున్నట్లయితే సబ్స్క్రైబ్ చేసుకోండి, వీడియోని లైక్ చేయండి, మీ ఫ్రెండ్స్ తో షేర్ చేసుకోండి. సిఓఏకి సంబంధించిన అన్ని వీడియోస్ ఇందులో వస్తాయి. మైక్రో ఆపరేషన్ ఈ రోజు టాపిక్. మనం ఇంతకుముందు రిజిస్టర్ ట్రాన్స్ఫర్ లాంగ్వేజ్ గురించి తెలుసుకున్నాం. వాట్ ఈస్ రిజిస్టర్? రిజిస్టర్ ఈజ్ ఏ కలెక్షన్ ఆఫ్ ఫ్లిప్ ఫ్లాప్స్ అండ్ ఈచ్ ఫ్లిప్ ఫ్లాప్ క్యారీస్ 0 or 1 అనే డేటా. అయితే ఇక్కడ ద బేసిక్ ఆపరేషన్ which is performed on data which is stored in registers is called micro operation. సింపుల్ గా మనం రిజిస్టర్స్ మీద పర్ఫామ్ చేసే చిన్న చిన్న బేసిక్ ఆపరేషన్ ని టాస్క్ ని మనం ఏమంటాం? మైక్రో ఆపరేషన్స్ అంటాం. సో సింప్లీ మైక్రో ఆపరేషన్ ఈజ్ అన్ ఆపరేషన్, బేసిక్ ఆపరేషన్ which is performed on register data. Means the data which is stored in registers, on that data we are going to perform some operations. That operation is called as micro operation. So these micro operations are mainly 4 types. First one is register transfer micro operations, arithmetic micro operations, logic micro operations, shift micro operations. These are the 4 types of micro operations in COA. Register transfer language or register transfer micro operation we have discussed in last class. Please go to my YouTube channel and visit COA playlist. Register transfer language RTL అని చెప్పేసి ఒక వీడియో ఉంటుంది. దీనికంటే ముందు వీడియో అది చూడండి. You will be clear about register micro operation. Today we are going to discuss arithmetic micro operations, logic micro operations and shift micro operations. Arithmetic micro operations. These operations deals with the operation performed on numeric data stored in the register. So register లో స్టోర్ చేసినటువంటి న్యూమరిక్ డేటా మీద పర్ఫామ్ చేసే ఆపరేషన్స్ ని మనం ఏమంటున్నాం? arithmetic micro operations అంటున్నాం. The operations which are performed on numeric data which is stored in our registers. For example, arithmetic operations, addition, subtraction, increment or decrement. These operations are called arithmetic operations. Here you can see a simple table which represents all arithmetic micro operations like addition, subtraction, increment and decrement. Here R3, R1 plus R2 will store in R3. Means R1 data and R2 data will be added and the resultant data will be stored in R3. This is simple addition operation in registers or micro operations. Same like that, R1 and R2 data will be minus and it will be placed or it will be transferred into R3 registers. So here R1, R2, R3 are any general purpose registers. Here R2 bar shift to R2 means the complement. So R2 bar is called as R2 complement. So complement will be represented like this, R bar or R dash. Sometimes we represent R bar, sometimes we represent R dash. Anything is called as complement of R. Okay, it is 1's complement. What is 2's complement? 2's complement is 1's complement plus 1 is called as 2's complement. The 1's complement plus 1, the resultant data will be shifted to or transferred to R2. And here R1 plus R2 bar plus 1 means this is subtraction operation and it is also called as XOR operation. So you know that XOR gate, right? XOR gate. Okay, that XOR gate operation is stored in our computer registers like this. Whenever you have to perform the XOR operation, you are going to perform, suppose you want to perform A and B XOR operation, then what you have to do? A plus the second number, B bar plus 1, means you have to add first number with the 2's complement of second number, then it will become the XOR operation. That XOR operation will be shown like this. XOR will be, this is the XOR symbol, and the XOR B operation is called as A plus B bar plus 1, means A plus 2's complement of B at a first number plus 2's complement of second number. Here first number is R1 and the second number is R2. The 2's complement of R2 will be added to R1 and it will be stored into R3. So this is subtraction operation with the help of only additions, and it is also called as XOR operations. And R1 plus 1, it is called as incrementer, and R1 minus 1, it is called as decrementer. So these are the simple arithmetic operations, and in next slide we are going to discuss everything related to this addition, subtraction, incrementer, decrementer with the help of hardware implementations. In arithmetic micro operations, first we are going to discuss about binary adder. A simple binary adder is a digital circuit that performs the arithmetic sum of two binary numbers provided by any length. So simply a binary adder is used to add two binary numbers with any length, means 4-bit binary numbers, 8-bit binary numbers, like this. Any length you can give it, do the addition of that binary numbers and give the result. Suppose I have given 0, 1 and another number 1, 0. Then what does the binary adder do? Means it adds these two numbers. So like this, 0, 1, 1, 0, 1, 1. The resultant value will be 1, 1. What is 0, 1? 1. And what is 1, 0? 2. The resultant will be 3. Okay, like this binary adder do the addition of any two binary numbers with any length. So in previous example I have given only 2-bit numbers, like this it can do any length numbers. Okay, a binary adder is constructed using a fully adder circuit connected in series with the output carry from one fully adder connected to the input carry of the next fully adder. So I will explain this clearly with the help of example diagram, don't worry. Here, so this is the simple 4-bit binary adder hardware implementation. So in this you can see we have 4 fully adders. So why? Because I am using 4 fully adders, means I am taking 4-bit binary adder. Suppose if I use 8-bit binary adder, I have to take 8 fully adders. So each fully adder takes the input, like suppose I have taken two numbers as A and B. So in this A and B, the 4 bits in A number will be A0, A1, A2, A0, A1, A2, A3. And the 4 bits in B number will be, and B binary number will be B0, B1, B2 and B3. Here I am sending each time 1 bit from A and 1 bit from B, and it will be added and result will be S. Suppose if I send A0 and B0, means the rightmost bit, least significant bit of A and least significant bit of B will become the least significant bit of sum. And initially there is no carry. Suppose I am taking example here 1, 0, 0, 1, and this is 1, 1, 0, 0. Like this two numbers I have taken. This is A0, A1, A2 and A3. This is B0, B1, B2 and B3. So now I am adding these two, A0 and B naught, and sum will be S naught. Next, if I add A1, B1, the sum will be S1, and A2, B2, the sum will be S3, and A3, B3, the sum will be S4. Every time whenever I add A naught and B naught, if any carry gets, అంటే suppose ఇక్కడ 1 and 1 ఉంటే carry వస్తుంది కదా, that carry will be added to next full adder, which is I am showing here as C1. If I do A naught plus B naught, means this number plus this number. If it is 1 and 0, no problem. If it is 1 and 1, carry will be get. Okay, so that carry will be given as input to next full adder. So ఇక్కడ ఇస్తాం కదా ఇక్కడ. So this is the carry is input to the next full adder అన్నమాట. Okay, like this binary adder will work. So here I will explain everything. The organ bits A and addend bits B. So మనం 2 numbers తీసుకోవాలని చెప్పినాను కదా. I am considering one as organ and the second one as addend. ఇవి రెండు కూడా నేను ఎలా చూపిస్తున్నాను అంటే ఆర్గన్ బిట్స్ ని A0, A1, A2, A3 లాగా చూపిస్తున్నాను, అండ్ addend bits ని B0, B1, B2, B3 లాగా చూపిస్తాను. ఓకే, ద క్యారీ ఇన్పుట్ స్టార్ట్స్ ఫ్రమ్ C0. అంటే ఫస్ట్ లో మనకి క్యారీ ఏమి ఉండదు కాబట్టి ఇట్ విల్ బి స్టార్ట్ యాజ్ C0, అండ్ ఆఫ్టర్ యాడింగ్ A0 plus B0, if carry gets we call it as C1. After adding A1, B1, if carry gets we call it as C2. Like this carries will be C0 to C3, and this finally is output carry, and everything connected in a chain to full adders. Next, the output carry from each full adder is connected to the input carry of next full adder. What I say already explained about this. Every carry will be given as input to next full adder. Next, the sum of outputs S0 to S3 generates the required arithmetic sum of digits. Whatever we get S0, S1, S2 and S3, these are the required result of A plus B output. Okay, the n data bits for the A and B inputs come from different source registers. For instance, data bits or a input comes from source register R1, and data bits for B input comes from source register R2. So I am storing these A bits in register R1, source register, and I am storing B bits from R2, the source register 2. And the final point, the arithmetic sum of the data inputs A by can be transferred to R3 register, one of the source register. Simply what I am saying here, R1 plus R2, the result will store in R3. The result will be transferred to R3. This is transfer symbol. దీన్ని మనం రిప్లేస్మెంట్ సింబల్ అంటారని లాస్ట్ క్లాస్ లో నేను చెప్పాను. ఓకే, సో దిస్ ఈస్ బైనరీ యాడర్. అర్థమెటిక్ ఆపరేషన్స్ లో సింపుల్ బైనరీ యాడర్ గురించి, 4-bit బైనరీ యాడర్ గురించి మనం నేర్చుకున్నాం. సో ఇన్ దిస్ క్లాస్ వీఆర్ గోయింగ్ టు డిస్కస్ అబౌట్ బైనరీ యాడర్ అండ్ subtractor. So binary adder, subtractor. So in last class we have discussed about binary adder only. Here I wanted to do addition and subtraction micro operations using single hardware implementation. Okay, so here we can see single hardware implementation for adding and subtracting two binary numbers. Okay, so a subtraction micro operation can be done easily by taking the 2's complement of addend bits and adding to the organ bits. So నేను ఇందాకనే చెప్పాను already, in COA if you wanted to do subtraction operation, you have to do first number plus 2's complement of second number. What is the second number 2's complement? B bar plus 1 means 1's complement B bar plus 1 will become the 2's complement of B. Here if you want to do subtraction operation, you have to do XOR operation. So that is, you have to do you have to take 2's complement of second number and you have to add that one with the first number. Okay, so the arithmetic micro operations like addition and subtraction can be combined into one circuit by including exclusive OR gate with each full adder. సో మనం లాస్ట్ క్లాస్ లో చెప్పుకున్నటువంటి ఫుల్ యాడర్ 4-bit బైనరీ యాడర్ ఉంది కదా, దానికి XOR గేట్ ని యాడ్ చేయడం వల్ల, why I am adding XOR gate means I want the 2's complement of second number to make subtraction operation in COA. So to make that subtraction operation I am adding an XOR gate to each and every full adder. Okay, and so you here I will show the simple arithmetic binary adder and subtractor hardware implementation here. So whatever the diagram we have seen earlier, that this is the part, okay, same, but for everything I am adding an extra XOR gate. Why? Because if I want to do XOR operation, sorry, subtraction operation, I want to perform XOR. Okay, so that's why I am adding an XOR gate to each and every full adder, and this will be mode bit. So this mode bit will says what is the operation I have to do. If mode bit is 0, I have to perform plus operation, means addition operation. If mode bit is 0, I have to perform subtraction operation. Like this it will be. So అంటే నేనున్న ఈ కాంబినేషనల్ సర్క్యూట్ లో I can perform addition and subtraction, and at a time I can perform one operation. So that one operation will be decided by the mode bit M. If mode bit M is 0, I have to perform plus operation. On that time XOR gate will be in off stage, and if M bit is in 1, if M bit is 1, I have to perform XOR gate, subtraction operation. On that time XOR gate will be on. Okay, so if XOR gate మనం చేస్తున్నాము అంటే for the subtraction operation, XOR gate చేయట్లేదు అంటే that is for the addition operation. Okay, so here we will discuss everything about this also. So here when the mode input M at low logic means it is 0, the circuit act as adder, and when the mode input M at high logic means 1, the circuit act as subtractor. As earlier I told this only, if M is equal to 0, I have to perform addition operation. The combinational circuit works as a binary adder only. If it is M equal to 1, it works as a binary subtractor, means XOR gate comes into the play. So the exclusive OR gate connected in series receive input M and one of the inputs B. So this M mode will be connected with series exclusive or 4 gates are there in above diagram. That 4 gates will be connected in series along with B bit bits. So why I am using only with B bits means I have to do the 2's complement of B register only, not the A register. That's why I am connecting exclusive OR gate with only B inputs along with XOR gate. Okay, so here when M is at low logic, we have B exclusive OR 0 equal to B, means we are going to perform the 2's complement of B here. The full adders receive the value of B, the input carry is 0, and the circuit performs A plus B. So if M equal to 0, what we do? We don't do any 2's complement or anything. We are directly going to do B plus A. Okay, and input carry, initially input carry will be 0. Okay, next when M equal to 1 at high logic, we have B exclusive or plus 1, that is equal to B bar, and C not equal to 1, means carry will be 1. So B input are complemented and carry will be added to that complemented one, that is B bar plus 1. It means 2's complement of B. So like this we perform binary addition and binary subtraction in single circuit, combinational circuit we call it. In this class, we are going to discuss about binary incrementer in arithmetic micro operation. The increment micro operation, you know that in C language, in C++ we write I plus, right? So this is increment. So same operation will be performed in COA in binary form, that is called binary increment. For doing this operation, binary increment, we use binary incrementer and hardware implementation called binary incrementer. So the increment micro operation adds one binary value to the value stored in register. So whatever the value stored in register will be incremented plus 1. Okay. For instance, so a 4-bit register has a binary value 0, 1, 1, 0. So now I am going to increment this register with 1. Then the value will be 0, 1, 1 and 1. Why? Because I have incremented that one. Next, the increment micro operation is best implemented by 4-bit combinational circuit shown below. Whatever the binary incrementer I am saying, which is used to increment 1 with the given register, is shown in below diagram. For this we are going to use half adder. We are not going to use full adder. Why? Because we are not going to use 2 registers, 2 inputs. We are going to use only 1 register. So half adder is enough. So I have taken 4 half adders, like same in binary adder I have taken 4 full adders, right? Same like that I have taken 4 half adders, and I have a register called R, and in that I have stored A0, A1, A2 and A3, and A0 will be connected with the first half adder, and A1 will be connected with the second half adder, and A2 will be connected with the third half adder, and A3 will be connected with fourth half adder, and each bit will be connected with half adder, and the output will be S0, S1, S2 and S3, and each and every carry will be connected with next one, and we are adding 1 with the least significant bit of A. So A lo unna least significant bit ki manam 1 add chestunnam. Incrementer means we are going to add 1. So that will be first half adder A0 ekkadaithe undo daniki manam 1 add chestunnam, and sum will be S0 if carry will be given as input to the next half adder. So and that will be added with A1, and if carry gets, that will be added to the next half adder. This will be continue up to the end of binary bits. Like this we are going to perform binary increment operation using 4 half adders in COA. Here a logic 1 is applied to one of the inputs of least significant bit of half adder. So as I said, A0 ki manam 1 add cheyali, least significant bit antam manam A0 ni, and other input is connected to least significant bit of the number to be incremented. Okay. Next, the output carry from the 1 half adder is connected to one of the inputs of the next higher order half adder. So the output carry of the 1 half adder will be added to the input carry of the another half adder. The binary incrementer circuit receives 4 bits from A0 to A3, add 1 to it, and it generates the incremented output of S0 to S3, and the incremented output will be stored in S0 to S3. So this is arithmetic micro operations completed. Okay, in next class we are going to see logical micro operation.